So I accidentally hit stop recording versus pause recording. So there's going to be more parts than I thought here. So what's an example of an inverse function? Well, here's just a quick example here, idea. So let's let f of x be x cubed. What does f do to something? Well, f takes what you plug in, and it is going to raise it to the third power, multiply 3 copies of your input. Okay, so I'm going to plug x. So I'm going to plug x into f, and what comes out is f of x, which is equal to x cubed. So whatever the input was, now the output is the cube of the input. Now what can we do? What would be the inverse function here? What function g would undo what f just did? So if I tell you that I cubed something, right? So I cubed something, and then I got 8. Can you answer that question? Can you always figure out what you can cube to give whatever the output was? So if I cube a number, get 8, can you answer that question? Well, if you think a little bit, and you can pause this video and think about it, what can we multiply 3 copies of that gives 8? And then you might come to the realization that it's 2, because if I do 2 times 2 times 2, I get 8, right? So I can undo the cube, and in fact, we can apply the same idea to a negative number. So what do I cube? What do I cube that gives me negative, say 27? And if you think about it for a little bit, again, pause the video if you want to think about it. What number do you multiply 3 copies of, and it would give you 27? Well, you'll end up with, and again, pause it if you haven't figured it out yet, negative 3. All right. So given the output and the function, can you figure out what the original input was? If you can always answer that question, always, every time, then that means that function has an inverse. You can undo it. Okay. So if I plug it into g, where g of x is the undoing of the cube, what undoes a cube? That's the cube root. Right? The cube root cancels the cube out. So g, if I were to plug x cubed into g here, that would be the cube root of x cubed, and that just gives you x. Because remember, odd roots of the same odd power, they cancel perfectly. If you're taking even roots of even powers, unless there's some domain restriction, you end up with absolute values around that input. So that's an example for another time. But the whole point here is that there's a way to undo what f did. So if you feed something through this machine or function that we call f, and you see what the output was, you could kind of unbake or unravel what f did to go back to what you started with. And I'm probably repeating myself a lot, but that's the whole point of an inverse function. So here, f of x, the function f at the input x is equal to x cubed. That's what f does to the input, cubes it. And g of x is equal to the cube root of x, are inverse functions. Okay, that's kind of the whole idea. So if there's a way to undo with what you did, then there's an inverse function to that. But it has to be true in both directions. So if both 1 and 2 are true, then, so if you can do it in either order, then we say that those functions are inverses. So let's just look at one more before we finish our intro here. So let's say f of x is this function, x plus 2. Actually, I'll do a couple more examples after this, so verifying that 2 functions are inverses. This is probably one I should have started with. It's a bit simpler. So if you add something to a number, if someone says, hey, you know, you gave me some amount of money and I added 2 to it, then I had $10. Right? He has or she has $2 in their pocket, and then you gave them $8, right? So you can figure out. So I screwed up that example. Sorry. If someone has $2 in their pocket and you gave them some amount of money and you don't remember how much you gave, that's the input, right? That's what F does. It adds a number that it adds to whatever you're plugging into F. So if you gave someone money and they put it in their pocket, and they told you that they had $2 in their pocket, then they pulled out their money and they said they had $10. Could you figure out what you started with? And the answer is yes, right? Because if you know that you're just adding 2 to a number, how do you undo addition by 2? You just subtract 2, okay? So that is how we undo this one. So if we wanted to find the inverse function here, so x goes into F here. We're going to go into in the next video how to find inverses. So that's not the point in this video. But if x goes into this function F, we know that F of x is going to be 2 more than what was plugged in. And then that, if we plug it into the function g, which, just intuitively, if you think about it, we're subtracting 2 instead of adding 2. I don't know why I wrote that as 2 plus x instead of x plus 2. It doesn't matter, but let's fix that up there. So g, if that's a subtraction function, if I'm subtracting 2, so it takes whatever is there and subtracts 2 from it, then we're going to be able to see that we go back to what we started with. So g, what comes out of g is g of f of x. And then just like we did with compositions, we can simplify this. So g of x is going to be x plus 2. So g of anything is that thing minus 2. So in this case, it's going to be f of x minus 2. Right? If we're plugging something into g, it just means we're subtracting 2 from it. And in this case, I can just replace f of x by what I'm plugging in. So I mean, the formula for f of x, that's what I'm plugging in. That'll be x plus 2 minus 2. And that'll just be x. Now, this isn't a complete proof that f and g are inverses. Technically, you should show the opposite is also true. So here's a little exercise for you. So show that f of g of x equals x also. What we just did, this is g of f of x. We showed one direction of the composition, but we didn't show both of them. Right? So once you show that both of those are true, then you're showing that they're true inverses of one another. So let's do a couple of examples just verifying, and that'll conclude this first video. Just a couple quick examples of showing that two functions are inverses. So let's show that, let's see here. Let's say f of x is equal to 2x. We'll start off really simple. F of x equals 2x, and g of x is equal to 1/2 x, 1/2 times x, right, are inverses. I chose this one because it's really intuitive, because if you double something, how do you undo that? You take half of it, right? So if you double your money, how do you go back to what you started with? So if your money goes up 100%, it's going to have to go down 50%. So these are inverse functions just kind of on an intuitive level. If you think about it, I mean, I know I'm talking quick, but think about why they might be inverses, and it might become clear. But let's show it formally. To show it formally, anything in mathematics to show or to prove, those are kind of synonyms in this case, that they actually are inverses. You have to show two things. You have to show that f of g of x is equal to x. So we want to show, and also we want to show that g of f of x is equal to x. So once we verify that both of these are true, then we're done. Okay. So let's actually show this. So let's show that f of g of x, remember the definition of that, that is f parenthesis g parenthesis x. So we're plugging g into f. And what does f do to the input? Well, from the definition of f of here, it just multiplies whatever you're plugging in by 2. So f takes 2 times whatever you're plugging in, and we're plugging in the expression for g of x, which is 1/2 times x. Now in this case, the 2, so just we're algebraically simplifying at this point. The 2 and the 1/2 will cancel, just putting a 1 in the denominator, 1 in place of the 2. So we just have a 1 in front of x at this point, so we have an x. Done. All right, easy enough. Now let's verify the second one here. G of f of x. Now we're plugging f into g, so we're looking at g of f of x here. So what does g do to the input? Well, again, going back to the original definition of g, it multiplies 1/2 by whatever you're plugged in. So g is going to take 1/2 of whatever is plugged in. In this case, we're plugging in the expression for f of x, so that's going to be 2 times x. And kind of the same thing, but in the reverse order, the 2 and the 2 will cancel. 2 in the numerator in the parentheses, and the 2 in the denominator outside the parentheses, those will cancel, and we'll just be left with x. Only when you show both of these are true have you actually verified that they're inverses. So you do have to go through the algebraic manipulations and steps to actually prove that they're inverses in every sense. Do not plug in numbers. I've seen that in the past, that people may have learned from different sources where they just plug in a bunch of different numbers and say, hey, they're inverses. Don't do that. What you want to do is just general variables and show that both are equal to the original input. So here's the point here. The point here is that since f of g of x and g of f of x are both equal to x, f and g are inverses. This is the type of work that I expect if you're trying to show that two functions are inverses, and that's basically it. I'll do one more example. So let's show that another word they use is verify that f of x is equal to, let's say, 2x plus 1 over 5, and g of x is equal to 5x minus 1 over 2 are inverses. And there's actually a pattern to this. If you wanted to invest time in investigating, I just made up this example off the top of my head. If you can quickly solve a simple algebraic equation for x, like what would you need to get x by itself? Well, first of all, you'd have to multiply by 5, right? So if you're just looking at f of x here, first of all, to get x by itself in that expression, you'd first have to multiply by 5 to get rid of the denominator. Then you'd have to subtract 1 to get the 1 out of the numerator. Well, there's no more numerator, it's just the whole thing. Then finally, x by itself, you'd have to divide by 2. Now, maybe you have to rewind this to hear what I said out loud again, but that is exactly the expression for g of x. So to undo what a function algebraically does to an input, you just unravel it using PEMDAS in the reverse order, kind of. So you are solving for the variable. If you heard my phone, I apologize about that. So let's just verify that these two are actually inverses. So once again, we're going to show that f of g of x, which is f of g of x, that's equal to x. So we're showing this is true. So is that true? So let's compute it. So f of g of x, which is f of, or evaluated at, the expression g of x. And that's going to be f, or what does f do? Whoops. What does f do to the input? Well, it takes so looking up here at f takes 2 times the input, adds 1 to it, whatever the 2 times the input is, and then the entire result of that, it divides by 5. So we're going to do 2 times g of x. What is g of x? Well, that is the expression 5x minus 1 over 2, right? That's g of x. And then so 2 times g of x plus 1, and we're going to divide that by 5. All right, so if you need to, take a second to think about what I just did. Right, I'm plugging g of x, the expression for g of x, the output, into f as the input for x. So think about how I arrived at that expression. And then if you're okay with that, we're just going to go ahead and simplify step by step. Please do not just write that this is equal to x. We have to show it step by step. So in this case, the first thing, if we follow PEMDAS, we're going to first, well, not PEMDAS, sorry, just standard cancellation. Here, the 2 and the 2 in the bottom, they're going to cancel. And we're going to end up with just the numerator there, so 5x minus 1. Technically, those parentheses are no longer necessary because there's nothing to distribute. There's no exponents. So we can just pretend like these parentheses here are actually not there. So that'll allow us to cancel the minus 1 and the 1, giving us 5x divided by 5. Then finally, the 2 5s will cancel like factors in numerator and denominator, and that gives us x. Okay, so that is how we show that a composition simplifies to the original input. We have to take it step by step and show the end result. This is what constitutes full work. This is what constitutes full credit for a problem like this. So question 2 here, criterion 2, we're going to look at g of f of x, and we're going to fully simplify this guy here. This is g of f of x. And if you want to pause this and go ahead and see if you get the right answer, that's cool too. So what we're going to do is we're going to plug f into g. So I'm going to start with g. What does g do? It takes 5 times whatever I'm plugging in. It subtracts 1 from it, and then it divides the entire result by 2. What are we plugging in? We're plugging in f, the expression for f of x, and that's 2x plus 1 over 5. So it's 2x plus 1 over 5. So this is going to be very similar to what we just did. So it's like more practice than we just did. So first, the 2 5s are going to cancel. Then I'll end up with 2x plus 1. And, well, technically in parentheses, but you don't need them. There's nothing to distribute, right? Just like before, over 2. Then the positive 1 and the minus 1 will cancel, giving us 2x over 2, which will give us x. So, yeah, I mean, the intuition here is that if you're looking at f, what does f do? It multiplies something by 2. Whatever this something is what you're plugging in. So you multiply it by 2, you add 1 to it, and then you divide the whole thing by 5. How do you unravel that? How do you get the x back from that expression? Well, first you get rid of the 5 in the denominator. You have to multiply by 5. Then you subtract the 1 away. That'll leave you with the 2x, and then finally dividing by 2 will isolate the x for you. So that's kind of the intuition for inverse functions, or at least my intuition for it. You might have a different intuition if you explore this on your own. But that's the intro, and that's the definition for inverse functions. So I'll leave the video where it is now, and then I will go into in the next video how to find inverses of functions, and then maybe one more video on something called the horizontal line test. We already looked at the vertical line test, but the horizontal line test is a bit different. So some information on the graphs of functions that have inverses and the graphs of those inverses. So we'll stop there and you can check out the next video once you're ready.